Hey, Algebra 2 students, this is Mrs. Bird. This is a tutorial or a walkthrough of the questions that you see in Lesson 5 for Project 1. So I'll be walking you through these questions for this. My suggestion is always to, you can open this video in a separate tab as you do your own project, or even if you're fancy, you can do a side-by-side, kind of like what I'm doing here with your project on one side and this video on the other. So do what works for you. You do you, man. All right, jumping into number 1, it's saying to think about this statement. The difference of squares of two integers in the length of one leg of a right triangle. Twice the product of those integers is the length of the other leg of the right triangle, and the sum of the squares of those integers is the length of the hypotenuse of the triangle. What? Well, this is actually a little bit more important information to begin with. It says, let the length of one leg of a right triangle. Okay, so that right there, I'm going to draw a right triangle. So it says, let the length of one leg of that triangle be A. So one of these legs be an A. The length of the other leg be B. And the hypotenuse is C. So at least I'm starting to visualize what these words are talking about. And then it also goes on to say that X and Y are integers, which are really just numbers. They are numbers. Okay, so now let's jump back up to that first mumbo jumbo, and it will start to make a little bit more sense now that I have a visual representation of those of that triangle that this first little paragraph was talking about. So let me see if I can, we are going to dissect it piece by piece. It says the difference of squares of two integers. So I'm going to pause there. Remember, we already know two integers. X and Y are those two integers. So I'm seeing the difference, which really is just a fancy way of saying subtraction of squares. So I'm thinking squares. I'm not thinking about the actual geometric shape, but I'm thinking about the exponent of 2 here. Okay, so I'm going to just start right there. The difference of squares of those two integers. So my integer x and y, if I combine that together, it would be the square of x difference with the square of y. I'm squaring those two integers, okay? So see, it's kind of like a little mystery. We just take it down piece by piece. Is, whenever we see the word is, that means equals the length of one leg of that right triangle. Oh, okay. It is, so that's our equal to the length of one of these legs. Now, it doesn't tell us which leg it's talking about. It could be the leg of A or B. You get to choose. So I'm going to just choose one of them and say that's A. So I'm going to just actually add that to my diagram. So again, you get to choose what x squared minus y squared is equal to. You can set it equal to A or B because both of those are legs and it doesn't specify which one it's talking about. Okay, so now, comma, it's like it's setting up a new equation or a new little formula here. Twice the product. Okay, twice the product, twice is 2, product is times. So 2 times those integers. Hey, we already know what those integers are. So it's going to be 2 times those integers, which we know to be x and y. Okay, now we're jumping back to is the length of the other leg of the triangle. Okay, so the other leg, the leg that we have not used so far, is B. So that has to be equal to b. So again, I kind of like to fill in everything in my diagram as I do it. Okay. What's another fun color? Maybe that light blue for that shadow. Okay. All right. And all right, new one. The sum, meaning adding. So I'm adding, the squares. So exponent of 2 again of those integers. Okay. So I'm adding the squares of those integers. So integer x squared, add with the integer of y squared. Going on to finish is the length of the hypotenuse. Oh, what up, C? That's my little hypotenuse, my little hypoteni is C. Okay. So what question number 1 is asking you to do is kind of dissect this fancy wording that we have right here. Take all of those words and write them in math equations. See, this is why I love math. Look at all those crazy words over here. Give me that any day. So question number 1 is matching these formulas or these equations that we just wrote from that wording. Now, remember when I said that x squared minus y squared, this could be an A or a B because it did not specify which leg it was talking about. So there actually is 2 correct responses there. We could have had an x squared minus y squared equaling B, the other leg, which would have left 2xy equaling A. So we could have swapped A and B, but x squared plus y squared always has to be the hypotenuse, which in this case we labeled that as C. So here are your 2 correct responses that you're trying to match in number 1, in the blue and the green. Okay, so that's question number 1. Question number 2 is using the exact same statement that we just dissected here. So I left that work up there for a reason. And now it's saying which equation correctly represents the relationship between A, B, and C in terms of x and y. So which equation represents? You're matching these equations. I'm not. I'm just showing you where these comes from. These comes from. That was good. That was good English, Bird. That was good. I'm going to show you what the wording means. So which equation correctly represents the relationship between A, B, and C? Oops, I didn't mean to cross that out. So A, B, and C. Come back to what do we know about A, B, and C, or what do we understand about A, B, and C? Well, don't we know that A, B, and C are A and B are the legs of the triangle, and C is the hypotenuse. I can see that because of my diagram. Now, you might recall something really important about A, B, and C in that right triangle. Again, right triangle. You might recognize the Pythagorean theorem. Good old Pythagoras. So the Pythagorean theorem says that if I have one leg and square it, adding that with the other leg and square that, it has to be equal to the square of the hypotenuse. So at least I was able to take those A, B's, and C's and write one equation where they were all related together. So now I want to follow up, but I want to replace A, B, and C with my X and Y relationships. So how am I going to do that? Well, luckily, we already have all of these relationships that relate that A to our variables X and Y. So that's pretty handy already. We've already done a lot of that work. So look in here, I can recognize that A, well, that's right here. So I can replace A with the x squared minus y squared. So I'm going to do that. A gets replaced with an x squared minus y squared. But remember, in Pythagorean theorem, that a value is squared. So it looks like a whole bunch of exponents of 2 there. And I'm going to add that with the square of b. So I just need to replace whatever b is equal to here. And b, there's my b, that's equal to 2xy. So I replace or use that substitution rule for b. And now that's going to be equaling c, but whatever c is, I need to square that still within the Pythagorean theorem. So looking up at the top, I got c. Oops, I've already used that green. If you're a visual person like me, you really appreciate the colors. So let me see if I can find some colors for you. C. C is an x squared plus y squared, so I'm going to replace that here. Okay, and that is exactly what A is asking. Which equation represents A, B, and C? So I took an equation that represented A, B, and C, but I rewrote them so that there's only x's and y's in it. So then question number 2, which definition or theorem helped you write that relationship? Well, it was good old Pythagoras. Good old Pythagoras. Okay, so that is questions 1 and 2. And question number 3 builds off of the same information. So I'm going to not delete everything, but I'll just meet you back down in question 3. Okay, so pick it back up at question number 3. We're still building off of that same information that we dug up from questions 1 and 2. So just to recap, we had Pythagorean theorem, and we rewrote them in terms of x and y using our relationships that we got. So go back to questions 1 and 2 if you need to clarify. So what prince digit writes a 2-column proof showing that if we simplify this right-hand side of the equation, and by right, I definitely mean left. So if we simplify this left-hand side of the equation, he is trying to prove that it actually does indeed equal the right-hand side. So we're going to manipulate the left-hand side through this proof here. So number 1 in the proof is always the same, and it is always the given. Start with what you're working with. So number 1, we are taking x squared minus y squared, quantity squared, plus 2 times xy squared. That's our given information. So what we're doing now is going from our given information, and we're starting to simplify and manipulate it in some way. So how did he manipulate the left hand? He used the binomial expansion. Well, okay, so let's see if we can figure that out. Over here, we only have one binomial. X squared minus y squared is the binomial. 2x plus y is not a binomial. Binomials are separated by addition and subtraction. So since I got that minus sign, binomial. So what is he doing with that binomial? He's expanding it, which means square it. So I'm going to do a little bit of side work here, and we're going to just expand that out. I know that anytime we have an exponent of 2, it really means to multiply by itself. So now I can see that distributive property. So x squared times itself is not an x squared, it is an x to the 4th power. X squared times a negative y squared, that would become a negative x squared y squared. Okay, then we're going to distribute the y squared over there. Y squared times that's another, remember, multiplication, the order doesn't matter. So a y squared x squared is the same thing as an x squared y squared. Order doesn't matter when we're multiplying. And then lastly, get the y to the 4th. Okay, so if I simplify that, combine these like terms, they're just 2 of those terms. So that would be a negative 2 x squared y squared plus y to the fourth. So that's our step 2, is x to the fourth minus 2x squared y squared plus 4. So that was our binomial expansion, but we also have the remaining part of that formula. So don't forget to add 2xy squared. Remember, that was binomial expansion. Okay. So now what did he do to simplify to the next step 3? He used the power of a product rule. So power of a product means that if I have, I always called it a power of a power. If I have a power raised to another power, power means that you product or multiply these. So that's the property that he's using, which can be shown right here. Now, I showed you with a very visible exponent. This 2, the x, and the y all have an exponent. They're just not very visible. Super secret exponents of 1. So now when I use that product, I multiply those, and I get a 2 squared, x squared, and a y squared. And you know what? I'm going to simplify that 2 squared. If you don't mind, I'm going to just simplify it to a 4. Okay, and then don't forget we still have the rest of this mumbo jumbo to add. So I still have an x to the fourth minus 2x squared y squared plus 4, adding with that 4x squared y squared. So that was power of a product. Okay, so again, we're just simplifying this left-hand side. Step 3, what did he do? Combine like terms. Okay, so coming back to our previous step, which was step 3, any like terms, x to the fourth terms. Holy smokes, you guys. I just recognized that I had a mistake in here. I was not writing my y to the fourth. I was just writing the 4. So let me fix that right quick. That would have sucked. Boom. Okay. Little mistakes always catch me, but that's okay. I caught it. We're moving on. Okay, so no x to the fourths. What about any x squared, y squared terms? Yes. X squared, y squared term. And then we get the lone wolf of the y to the fourth power. Okay, so just combining those terms. I wanted pink. Dang it. X to the fourth. Negative 2 plus 4 becomes a positive 2, x squared, y squared, plus y to the fourth, and that was like terms. Combine or comb them. And then 5th step, which is completed in the proof, they factored. You recognize this is actually a perfect square. So it factored that guy to get question number 5. So what you're looking for in the answers or the responses there is this guy to replace step 2, this guy to replace step 3, or the blank 2. So this would be blank 1. This would be blank 2. Then this guy would be blank 3. Cool. All right. And number 4, number 4 is same information. We've already done all of that work for this wording right here. But based upon the relationship you determined in question 2, which pair of numbers satisfy these properties? Now, it does give you a whole list of possible solutions. So how do I check whether or not this number is a real solution? We're going to plug that in. So let me recall our relationships that we already had from number 2, and I'll write those down for us to reference. Okay, so I rewrote all of the information that we had from question numbers, actually combined questions 1 and 2. And I'm going to encourage you to use the list of information that you have to test whether or not any of these are solutions. So if I looked at 1 for the first possible solution, x equaling 4 and y equaling 4, what I would want to do is substitute those into this equation, this guy, and see if it actually works. So here I would get 2 times 4 plus 4 squared plus 4 squared minus 4 squared. Does that actually equal 4 squared plus 4 squared? Oops, 4 squared and then a square. Okay, so quick arithmetic here. I do have a calculator if I need it. Let's see, 2 times 4 is 8, times 4 is 32, square that is 1,024. Oops, I forgot that little square too. 4 squared is 16 minus 4 squared, which is 16, 0, so 0 squared is 0. Does that actually equal 16 plus 16, which is 32? Right? 16 plus 16 is 32. And then square that. So does that work? Yes, it does work here. So I got a check mark here for this guy. However, okay. So we just checked out x equaling 4, y equaling 4 within this equation of just x's and y's, and it does work. It is a true statement. 124 is indeed equal to, 1,024 is equal to 1,024. So it works in that last one, but what about all of the other relationships of x and y? Now, I'm really worried specifically about this first one. If I think about that one, knowing that x equals 4 and y equals 4, that means that I have a 4 squared minus another 4 squared that equals b, which is the leg of one of my triangles, or one leg of my triangle. So let's just see, 16 minus 16 is 0. Does it make any sense to have a triangle where one leg is non-existent? You would just have a flat line. There's no vertical at all to measure. So there's no triangle anymore. So this would not work in that first equation. Therefore, if it doesn't work in all of them, it is not a solution. So 4 and 4 does not work. Now 1 and 2, if you replace 1 and 2 with the x and the y in all of these, it will work. So I'm giving you one possible solution, x equaling 1 and y equaling 2. There is one more for you to find on your own, and you want to do that just by checking substitution as I shown here, but you want to make sure that it works and makes sense in all of these and all of those relationships there. So that is question 4. Now, question 5 is asking you to think a little bit further about this relationship that we've talked about throughout this entire part of the project. So can you generalize that statement? So can you give me a little bit more information about that statement? And it's asking you to maybe conduct a little bit of research on the internet for that formula, which is known to be Euclid's formula. So I want to encourage you to maybe go and check out this demonstrations from Wolfram's. Here you can kind of see that you can play around with those relationships. It used an M and an N versus X and Y, which is what we played with. But you can play around with different values and see what would still be true and what is not true. That slider is quite slow. So what's true and what is not true as you generate different values. So I'm going to leave you to process through that question number 5 on your own. And as always, reach out to me if you have any questions.